So I'm Daniel Temkin. I wrote a book called 44 Esolangs that collects esoteric programming languages I've been making since 2009. So I'm going to assume that most of you are new to the idea of esolangs, esoteric languages. So I'm going to start by talking about two of the best known esolangs by other people before me. Probably the best known, the most notorious of these languages is called brainfuck. It was created in 1993 for the Amiga by Urban Mueller, who created sort of the smallest compiler for a Turing-complete programming language, which just means a language that can perform any algorithm that can be run on a conventional computer. And he did it in 1/4 of 1K for the Amiga. And then he sort of promptly disappeared. He actually sort of like did this thing and sent it out to this mailing list about another esolang, and he hasn't really been that involved since then. But what's happened is, over the last 33 years, many programmers have figured out how to write a lot of different types of code in brainfuck. So what this language looks like, it's all written in punctuation. It just has these 8 punctuation signs, and they're all about moving back and forth in memory, adding one, subtracting one, and having a conditional loop, which I'll show you in a second. But so this is the Esolangs wiki, which is a collection of many esolangs, and it's sort of like the repository of it's really the best place to find out about esolangs in general. But you can see how brainfuck is described here. What does this actually tell us about it? It says that brainfuck uses an extremely offensive word in the English language. It tells us that brainfuck has an array of 30,000 memory cells. It doesn't give you any sort of idea of what it's like to use this language, or why people are drawn to this, or what this is sort of all about. So this was sort of my introduction to esolangs. I kind of became interested in these around 2007, and I was really sort of looking for more information about what are these languages about? Why are people making these? And I found the existing documentation wasn't all that great. So I started a blog called esoteric.codes, where I interviewed people about their languages, tried to draw more parallels between work by digital artists and poets that were working within the space of basically any sort of piece where you have to read the text of code to understand it, and looking at common themes across these types of pieces. So back to brainfuck for a moment. This is a brainfuck program, and this is what it's actually like to run this thing. So basically, there's 8 different commands. They're all represented by different punctuation marks. Plus adds 1, minus subtracts 1. This is a loop, and the angle brackets are for moving back and forth through memory. And so the thing that sort of becomes clear when you look at this language, so this is how it runs. We're just moving back and forth in memory. This is going to be a hello world program, but it's going to build up each of the letters by getting to their ASCII values. And then at the end, it'll print them. The period is the print sign. So basically, all of these individual pieces are really easy to understand, but it becomes a technical challenge of how you bring these things together to actually write code that does what you want. And what's happened over the last 30 years is that programmers have written more and more sophisticated brainfuck programs as sort of technical challenges to themselves, as a way of showing off a kind of technical wizardry. Someone at one point wrote a web server in brainfuck, which actually worked. It was extremely slow. It was not efficient at all. But yeah, so we got Hello World in the end. So one of the other sort of best known early esolangs came out in, I think, around 2003. And it's a language called Pete. Many people call it Piet, but it's actually pronounced Pete, like Pete Mondrian, who it's named for. And Pete does something really different. Code is an image, and you can see in this Fibonacci example here, this is the actual program to the left. And to the right, you can see how it's read. The instruction pointer starts at the upper left, it moves across, and then the change in color, basically in hue and brightness from one of these blocks to the next, are commands. And some of those commands tell it to turn direction. And so it'll move back and forth through the image. And this is also a Turing-complete language, which means that anything that you could write in Python, theoretically you could write in Pete if you worked on it long enough. But the thing that's sort of amazing about Pete is that you can see the early programs sort of look very similar to each other, but over time people started to sort of develop their own styles within it. Thomas Scotch created this image, which is the cover of a wonderful book called Speaking Code. He also made something that attempts to look like Mondrian, but of course Mondrian doesn't use like magenta and pink. And you start to get more sophisticated programs. This is a program that calculates pi, and actually the larger that you draw the program and the less pixelated the circle is, the more accurate it'll actually calculate pi to. So it's using an image of a circle to actually represent a circle in code, which is something that could only exist in a language like Pete. So this was the first language that really got me excited about Esolangs. And this is an example of a type of language that is called multicoding. What that means is there are two different ways to read this program. You can read it as an image, and you can read it as code. But what makes it multicoding is that those two readings impact each other. It becomes sort of a constraint set to create an image that is going to actually carry out the program that you want. And so it becomes a sort of challenge to the programmer to do something that relates the two in some interesting way. So the first language that I made in response to that was a language called Velato, where I did the same thing with music. And so the way the book is set up, I have what are prompts, not for AI, but for people, which are these short sort of poetic descriptions of languages. And in the second half, the ones that I've actually implemented, I have details about how those are carried out and what they look like. Language 0 is this language Velato, which was my first language, the music one. So I'll show you what Velato looks like. So first of all, I'm not a composer, but this is sort of my example of two different ways to write hello world. The important thing about this language is that it only cares about pitch and the order of notes. It does not care about rhythm, it doesn't care about timbre. If you have a chord that has a whole bunch of notes that are sounded at the same time, it only cares about the order that they appear in the MIDI file. So it gives a lot of room for the programmer to construct something that they should have a good amount of control over how the thing is going to sound. I'm not going to play you my examples because they're, not great. But I will play something by someone else, a Spanish composer who recorded a piece with an orchestra that apparently does something in Velato, although he's not saying what it does. And I don't have the MIDI file, so I'd have to actually convert his score to find out exactly what it's printing. He's keeping it kind of secret. He calls it Velato Cohen. We'll see if this thing plays. All right, I don't think we're getting any sound. You guys aren't hearing anything, right? Okay. All right, that's all right. Anyway, it's like a contemporary classical piece, and it has like a kind of thing, and it's like, basically, while I give a lot of room for composers to have a lot of control over how it sounds, what's ended up happening is most of the people who have written music for it really lean into what the Velato algorithms sound like and kind of explore that rather than try to reshape it. So like one thing is, it's a MIDI file, but only the first track is read as a Velato program. So you can harmonize with a whole bunch of other notes that will not sort of affect the actual programmatic nature of the program. And the other thing is you can change the root note. So basically what happens is you start off with the first note that you play sets the root, and then everything else is in terms of that, but you can keep changing the root note, even in the middle of a chord. All you have to do is play a major second, and then whatever you hear, whatever the next note is, becomes the new root. And so you can keep changing it back and forth. So these are just sort of the basic rules of Velato. So one thing about Velato and multi-coding in general is this type of Esolang resembles other types of constraint-based work. In some ways, it's a callback to work like those of the Oulipo movement, which was a group of, it was based around Paris, but it was a group of mathematicians and writers who created constraint-based writing projects. The most famous one is by Georges Perec, and the idea of his piece was to write a novel in French without using the letter E. It was translated into English, also without using the letter E, and this is how he's celebrated in Paris with his street, Place Georges Perec, which has no E's in it. And similarly, with languages like Pete and Velato, you have this sort of constraint-based system where you're trying to do something that fills these two different roles in a way that impacts each other and creates a set of constraints for the music or the visual piece that you're creating. Now, the very last language in the book is a very different version of the exact same language. It is also Velato, but for a very different purpose. So where Velato, it's sort of something that you would sort of carefully compose, you don't have to do it that way, right? And I decided to make something where you're writing Velato programs on the fly for a different reason. This is a Velato interface where you whistle. Oh, I think with sharing the screen, this is gonna, oh, it might come up. I think with sharing the screen, it's having a little bit of trouble. Let's let this load for a minute. The idea of this is that you start the interface, and this is a JavaScript based, it transcribes Velato into JavaScript. Oh, there it goes, okay. All right, good. So I'm gonna try to write something. I'm gonna try to assign an integer by whistling. Let's see if I can pull this off. It's not picking it up right now. I think it's having trouble with the screen share. Oh, probably it's probably not picking up the mic here, right? Because of the sounds. I'm gonna turn off the sound thing because it's not working anyway. There we go. Hold on, let me get some water. Oh, is that a third? Okay, good. Sorry, I almost have it here. There we go, all right. So basically what happened is the first one that I whistled, if you can see behind me, is setting the root. Then I am doing an assignment. You can see the let. And then this is the variable, and I'm saying it's an integer. And then these are creating 32, and that ends the integer. And so this way, you can sort of sit at work, maybe with a headset on, whistle to your computer. The person next to you can be doing that too, and you can kind of harmonize each other. And you can all be writing JavaScript without touching your computers. Okay, so the beginning of the book, before I get into the languages, I have this sentences on code art, which is building off of Salo Witt's sentences on conceptual art. And this is sort of like the closest thing I have to like a little manifesto about Esolangs in general and what I'm doing in the book. I'm gonna close this because I think it's like, yeah, okay. So part of it is the idea that for any definition of the term programming language, there's a language that sits on its border. And then the other thing is that code is code because it conforms to the grammar of the language. A computer is the person or thing that executes the code as the language specifies. In this way, the language defines everything else. So what I mean by that is, just like I was saying about brainfuck tells us what the computer, it makes it very clear what the computer is for brainfuck. It is a series of memory cells and it acts in a certain way, and our computer is basically simulating that. But every programming language is essentially the machine code for the virtual machine that it presents to the programmer. And so it gives us a lot of freedom in terms of what these languages do and how they function. And it doesn't always mean that that these languages have to work in a way that is sort of expected. So language one, a language that better reflects the power dynamic between programmer and machine. Each line of code pleads with an interpreter god to act. The gods ask not only for clarity, but for humility and sincerity of desire. So this is a language that I made thinking about the idea of control and the machine. There's this sort of fiction that we have as programmers that the computer is doing what we want, when obviously it's not, it's doing what we said, which is often somewhat different. When I'm writing code, I don't feel like I'm sort of in control, but more that I'm trying to sort of plead with the computer to do what I want. So I decided to make a language that makes it very clear. And this is a sample line of code. Father Zeus, defender of cities, defender of homes, defender of the traveler and of those far from home, please create a loop counting from 99 to 1 called beer loop. So this is the beginning of a 99 bottles of beer on the wall program, and this is how it's broken down in the language. You have to pick the appropriate god for who you're going to ask to carry out what you're asking, and then you have to give adoration, and the amount of adoration, like here, I'm calling him Master of Storms, Father of the Gods, Defender of Cities, and so on. There's like a lot of epithets that make up that adoration. And that's important because there has to be enough to make up for how petty the thing is that I'm asking for. And I'm asking for like a whole bunch of stuff here, like print this thing, then print this variable, now print this string and some more variables. It's like really sort of, it's sort of a lot for one line of code. So you really have to lay it on thick. And the other thing is, you can't repeat yourself too much. Like if you call Master of Storms, if you're asking Zeus for something a few lines later, you have to find like other epithets that you know, so he's not offended. And what happens is, if you piss off one of the gods, that god will like stop responding to anything you ask for the rest of your program, and it can really like wreak havoc with whatever it is that you're trying to do. So Zeus is good for kind of structural things. But if you want to declare a variable, you have to appeal to the mistress of memory, Mnemosyne. Ariadne is the mistress of the labyrinth, so she is who you call on for any sort of branching in the program, like if statements and calling to functions. And then finally, if you are closing out a block of code, something that's usually represented with like a right curly bracket, you would call on Hades to collect the souls of any variables that remain. So you can think of the virtual machine of Olympus as being the gods themselves and everything that they're carrying out. But there's also a weird way where it kind of feels like it's about AI, even though I wrote this language before prompt engineering was a thing, before most of these AI systems were available. Because you're sort of one level removed from writing the code. You're asking the gods basically to write the code for you. And I found that like a lot of the languages in this book ended up seeming to be about AI, even though they weren't. Entropy is language 5. This is a language that I created in, I think, 2010 or so. And it sort of flips on its head what esolangs, how esolangs usually look. Usually you expect esoteric languages to have a very unusual looking code, but to allow you to have control over what happens in the program. But with entropy, it does something different. It's very sort of ordinary, boring looking code. This is what this page looks like when you first get to it. But what happens is every time you access a piece of data, it changes slightly. So basically, if you touch a variable, it will go off a little bit, and it happens over and over again. So what happens is it gives you sort of a little window to get an idea across to the user of your program before your program falls apart. This is what 99 bottles sounds like in entropy. Hopefully you'll be able to hear this from here. Or not. Oh.
Of beer. Take one down, pass it around, 98.22402 bottles of beer on the wall.
So that's at the very beginning. It gets, more and more corrupted as it
Bottle
goes.
need a polars or 78.85985 bottles of beer. Take on DQWP, pass RHT a sound 77.94613 bottle of beer for up fuel.
So basically everything is a floating point number in this language, including all the strings. And so bottles becomes coddles and then cottler and so on as it goes on. Now if I can find the place somewhere around 23, 22, we get something a little bit different happening.
Kasse GSR en VPD 21.13552.
So it's decided at that point that it's no longer English but Dutch. And it kind of stays Dutch for a little while and then goes back to English eventually. So one thing about the, and I did a version of Eliza, the chatbot, which became Drunk Eliza. One thing about this language, so when you create, the other important thing that I sort of learned from Brainfuck, and the reason I mentioned that Urban Mueller sort of disappeared, is that it's a community-based practice. If you make a language, you put it out in the world, you don't really know how other people are going to use it. And very often they're going to use it in ways that you're not expecting. With entropy, originally this was something I'd written a compiler for. It was Windows only at the beginning. And then someone named Andrew Hoyer created a JavaScript version a few years later. And what was sort of interesting was that he reinterpreted things a little bit. He got rid of the way the code actually looks. He just made it straight JavaScript, but he kept all the behavior. Like he decided this is the important part is the way it behaves, not really how it's written with the square brackets and all that. And he was totally right. And JavaScript opened up a whole different way of using this because I can do stuff like this. You can even do visual stuff now with entropy. So eventually, as that version became dated, I ended up sort of updating it with now I always release entropy as a JavaScript version. And that's something that's sort of very cool about creating a programming language as an art practice is that you're always inviting people to sort of rethink it, and people will use your language in ways you're not expecting. So another example of that is my language Fatfinger. Fatfinger is actually a dialect of JavaScript. But it is a programming language where typos and misspellings are valid code. All names, whether part of the language or given by us, can vary with every use. So where entropy is a language where the code reads very clearly, but it behaves in this sort of bizarre way, Fatfinger is exactly the opposite. It will always run as proper JavaScript, but you can write stuff that's full of typos and it doesn't really matter. So the way that you use this is you have to include the library, and then anywhere you have a script tag with JavaScript misspelled, it goes into Fatfinger mode, and you can fill it with all sorts of misspellings. So it's vart instead of var, document with a bunch of Ks, write RIT3, and instead of X, it's XX. And it will decide that the closest thing it knows about to XX is X, and so it'll print that. This is not a very dependable language because things kind of change over time with JavaScript. So something that worked as Fatfinger one year might not the next year and so on. But if you want your code to really work super well, you probably shouldn't be using this anyway. And to me, this really sort of embraces the best side of JavaScript, which is sort of its chaotic nature as a language. So I released this, whatever it was, 2017 or so. And what happened was other people used it in ways that were very different from what I thought. Instead of writing code that was full of typos and so on, Jeremy Douglas, who teaches at UC Santa Barbara, realized that he could write code poetry with it declare a variable y, why, and then use it as who, so it's who and what and when, and that these will all resolve to y. So instead of the sort of sloppy sort of typing and getting away from being overly controlling as a programmer, which is sort of what I was thinking about, he decided to make something that was very deliberate with it, but use it for this kind of poetry where he could write something that reads more English-like and can still run as JavaScript. And he created a list of words called the fat dactyls, which are sort of variations of JavaScript DOM elements and keywords that should work. So instead of doing window.alert to get a pop-up, you can do window.angry or window.answer or window.basket. And as long as you don't have a variable that's closer to basket, it will actually work. One thing that we usually do with programming languages is we expect it to result in programs that we can run on our computer and do something. But that doesn't have to be the case. I created a programming language called past tense. It is a programming language that speaks only of the past, and it's meant to be used for programs, never to be run again. The thing about this is you can use this with any code written in a language that has English keywords in some way, which is most of the programming languages we have. So for example, this was a C# program, and I've run it into past tense, and the result is this: namespaced helloed world, public classed programmed, public static voided mained strong args, system consoled wrote lines helloed world. So basically anything that is a verb or can be understood as a verb gets turned into the past tense. That includes string, which becomes strong. Hello becomes helloed, because apparently you can hello somebody. Now this is unrunnable. So it is officially a past tense program in that you can no longer run it in C#. But if you follow sort of the rules of this language, if someone were to write an interpreter that understood this and was able to run this, then it would mean that this program was no longer past tense because it would be brought back into the present. So it's only past tense so long as it actually cannot be run. And I do have a converter online to turn your programs into past tense for people who want to do that. Another area of code that we sort of commonly assume that code should be written in text, but that obviously is not the case all the time. We've already seen Pete and Velato. I decided to create a programming language that is built just on structure. It is entirely made up of folders. The language is called folders. This is an excerpt of a Hello World program. And it is just the pattern of containment that matters here. So this, just looking at this, I can tell that there's only one command because there's only one top level folder. And then the first folder within it, alphabetically, the number of folders inside that folder, it sets what kind of command it is. And then the second one, it takes the actual expression that's passed to that command. And it happens to be a string because that's being set here, and then so on. These other folders are all spelling out the actual text to print to the screen. One of the nice things about folders is that in Windows, Windows will tell you that they take up no space on disk, which is obviously a lie. But here I've created 352,000 folders just to prove this to you, that it will tell you that it takes up 0 bytes. So, I've now given you the tool to be able to store all your data as, what's that? Free. Yeah, it's all free. It's like there's no, we all have infinite hard drives now. You can just store all of your data as strings in the folder names, and then all your programs are just folder programs, and then you have as much space as you need. It's only in Windows though. Other systems don't give this to you for some reason. Another idea that is So, with these languages, a lot of them are sort of poking at certain sort of common ideas of what code should look like, and they're all sort of working around the idea that because we can define the executor of code any way that we want, it becomes less and less important whether something is actually runnable on our computer or not. It still is a programming language. And of course, pushing against the idea of trying to find those places that are sort of the border of what people would consider a programming language or not. But what happens when you start creating languages like that is sometimes you create very sort of effective languages that are very sort of unreadable to many programmers, but become more understandable to non-programmers. So one example this is a very roundabout way of talking about this. I created a language called Rivulet. It is a programming language written in tangles of lines. Commands are inscribed in the turns each line makes as it flows down the page. And I have this whole thing about these strands don't split, which has to do both with the way it's written and the way that the code runs. So this is a Hello World program. This was not written by me. It was written by Joe Wood, who's a professor in London. This will print Hello World to the screen. And the way this works is, this is all written with pseudographic characters. So back before when we sort of had still like text-based interfaces like the one on the left, we were able to draw boxes with these sort of like pseudographic characters, like these box drawing characters that are sort of lines and parts of boxes that you combine to create these interfaces. And these live on in Unicode. As you can see on the right, these are the Unicode version of these. And so basically, I'm just using these in a different way. This is two different ways of writing the same, they're called glyphs, these sort of blocks of code. They can be to the left and right of each other or one above the other. The line numbers start over at the beginning of each glyph, and it skips line number 4 for reasons I'll get to in a moment. There's a good reason that 4 is not there. But anyway, all right, but what happens is you can then, it'll format the code for you and give you this sort of nice, clean version with the colors to make it easier to read. And this will, in fact, print Hello World to the screen. Part of the thinking behind Rivulet is the way that programs are like mazes. Usually with a maze, we're not in the middle of a hedge maze like what we see here, but we're looking at it from above, where we can see the entire thing, but we still have to sort of run it in our heads to follow the paths to figure out how to get out of it. And it's the same thing when we look at code. We can see the code, but until we're sort of thinking it through and running it in our head, we don't really understand what it does. This is a full Fibonacci program. And the reason it skips number 4 is that every line number, it's all prime numbers. And these strands basically take their meaning by the way that the hook that starts them is pointing. If it's pointing to the up or to the left, the way that they move back and forth through the space of the glyph adds or subtracts numbers from them. So in this first one, we have something that's adding a 2 and it's moving back, so you get like -3 added over and over again, and it adds 5. I happen to know that this is going to create a 0. And so what happens is there's many different ways to write the same thing. So at the top, all 3 of these are different versions of the same glyph. It's adding 0, which it's using just to space out so that the second entry becomes a 1. This is adding 1. This adds 1 by adding 2 twice and then subtracting 1 3 times. This one over here is adding 2 and then adding 1 and then subtracting 3. Adding 1 twice and then subtracting 3, yeah. So each one, so there's a whole bunch of different ways that you can do the same thing. But what actually ends up happening when you're writing code in this is that writing the code is not that hard. It's mostly just compacting things so it looks good, and that's like sort of the fun part of doing this, is just moving all these box drawing characters back and forth, trying to get something that feels really compact. So this is 5 different versions of a Fibonacci program. All right, let's see. Which language do I want to show you guys next? How about... So one thing about Python that I find disappointing is that it's all written left to right. This is a version of Python in the most Pythonic format, written to follow the path of the serpent. So this is written in Bootstraphodon, which is, and this is what some Python code looks like formatted in it. And this is what it looks like in the book, the page. So I'll just read you a little bit here about language 2. In this style of writing called Bootstraphodon, lines are inscribed back and forth across the page. After a left to right line, the next line is read from right to left. The act of reading is more efficient as each movement of the eye picks up new information, unlike a strict left to right layout where we dart our eyes repeatedly to the beginning of the next line. Through an entire lifetime, millions of eye movements and perhaps whole minutes of our lives are saved. So yeah, the whole little section on this language is written in Bootstraphodon. I happen to really like it, the idea of reading back and forth. And I do have, so oxplows.com, which is written here backwards, is a little site that I made that will format your stuff in Bootstraphodon for people who want to do that. Another multi-coding language I created 2012 or so is called Light Pattern. And this is a language where code is written as photographs. And what's interesting about photographs is that they carry a lot of information, and they always tell more of a story than the photographer is even fully sort of in control of, right? So this is a programming language where the code is written in changes in brightness, hue, and contrast from one photograph to the next. Now, the simplest program that I wrote for this is the null program. It attempts to do nothing by basically photographing a blank wall with red, green, and blue filters. And it gets darker and darker because that's what's needed to get it to continually do nothing. And it runs as long as it can until it gets black enough that there's not enough information to see if it's more red, green, or blue. Right, okay, so that's sort of like the simplest light pattern program. But thinking about what kind of programs would I want to write with photographs, I started thinking about the Fluxus event scores, especially the piece Fly by Yoko Ono, which is one that she had revisited many different times. So this is an instruction-based piece. The original instruction is just the word fly, which she wrote for Grapefruit in 1963. And she's done a whole bunch of variations of this. There used to be, as a billboard that tells us to fly, and sort of most famously as the film that follows this fly that keeps landing on this woman like over and over again. So there's no sort of singular interpretation of this. But sort of my favorite version of Fly is, I guess Ono used to put a stepladder on stage that was like just high enough that if someone were to jump off of it, they might injure themselves, and sort of invite people to come up and fly by jumping off of it. Which, of course, they don't really stage that piece anymore, which is too bad, because I think that Yoko Ono is more interesting when there's a little bit of danger, like with her early work, which is not really how she's shown as much now. But so I decided to sort of recreate Fly by taking my camera and just throwing it in the air over and over again, make my camera fly in such a way that it'll photograph the pieces that then a series of photos that will then print the word fly to the screen. So this is a Fly program. These numbers that are superimposed on it are the change in brightness, hue, brightness, and contrast. Color, forgetting. Brightness, hue, and contrast, yes. So hue, it's cycling through red, green, and blue, the overall contrast, and the darkness of the piece. And you can see some of them don't have numbers on it. That's when I had to sort of reset things because usually it got too dark, or I couldn't get the next photo the way I wanted to, and if you do a 2-2-2, it resets it, and then you can do whatever you want for the next one. It kind of resets the whole thing. Anyway, I used a very cheap camera, like a GoPro, so I wouldn't actually like risk any of my actual photography equipment. This is another Fluxus piece. It's by George Brecht. And it is the 3 lamp events, which is on, off, lamp, off, on. So I decided to use lamps with red, green, and blue bulbs and photograph them in such a way that they would print his score to the screen. So basically, with both these pieces, I'm performing their score in such a way that it will create the score. It's sort of like making it circular. And I've also shown this as a sculptural piece where I would install this and it would photograph people as they go by. This is reproducing a piece by Paul Thayer, which is actually a fork bomb, which will crash your computer, but it does it while writing a short poetic thing about the light passing in the afternoon. So I thought that was very sort of appropriate. So there's, it collects a whole bunch of different pictures of people sort of looking at the sculptural thing that's photographing them and then ignoring it. And meanwhile, it's collecting all these images that will eventually be a program that will crash your computer. So let's see. I guess I will show you valence. So one of the other things about most of the time what we do in programming is we try to write a program that has a singular sort of denotation to the computer itself. But that's not always what we want to do. So in English, we can create a sentence like, Billy saw the group with the telescope that has 2 different readings. It could be that Billy is looking through the telescope and sees the group, or it could be that the group was walking by with a telescope and Billy saw them. And it creates these 2 different sentence structures for the same sentence. So I decided to do the same thing in code, and I decided to use these ancient Greek math and unit signs, measuring signs, as sort of the 8 symbols that I would use for this, because they don't have very strong associations to us. And what happens in this language is that you can just start writing code, and it will have, you can write a program that will have 2 different readings. And every time you do something that is ambivalent in that way, it will actually split into 2 different readings. So this is the interface for it. And one of the nice things is you can just sort of like key mash also with your left hand and something will come out of it. And so already I'm sort of creating a whole bunch of different interpretations of this. So right now there are 36 different versions, and you can sort of put brackets around certain things, which locks down a little bit of the readings in different ways. So I think since I was just sort of key mashing, so then what happens is each of these has a whole bunch of different ways that they can be read. Each one is, first of all, a variable, and you can see for each one of them, each one of these programs, you can see the state of each of these signs and what value they hold. But then this first sign is both the number 0, it is the variable for that name. It also represents an integer. It's add or not, depending on if you're using it as an expression. And then you can also use it as a command to create a while loop or do add a sign. So each one of these has all these different sort of readings, and each one of them will split the program again in different ways. So the other thing about programming languages is they don't have to be languages that our computers are capable of actually simulating, of actually carrying out. And we see that with, like, say, quantum computing, right? We have a whole bunch of programming languages that we assume will be useful in the future, but we don't actually have machines for all of them in ways that can be carried out now. I have a number of languages in this book, which in my last minute here, I will find one that I want to show you. Okay, I think I'll do this one. Okay, this is one of, this is one which I have not actually implemented. It is to write your instructions on paper, burn them, and keep from the ashes only what is unique to their inscription. So basically the compilation process is the burning, and what is unique to their inscription is the carrying out of those instructions. Because if the instructions were, if it turned out exactly the same, then the instructions would not be doing anything. So this is one of the final programming languages of the book. So basically, I just want to say I am teaching a workshop on Sunday at TIAT nearby. So if people want to talk more about Esolangs, you're welcome to join for this. Just ask me about this after. I do have a few copies of my book, and here is all my info. Thank you very much. So I know we're trying to tie up. Do we have time for a question or two?
Yeah, I think we're good at the moment. So good again. Yes, any questions for anyone? Here we are.
Thank you, this is crazy. So many languages. If languages are interfaces with your computer, how do you see the programming languages of the future?
Yeah, so I think that, you know, again, you're communicating with something when you write code. But the computer is more of a tool. The way that I see it, the computer is a tool that simulates the sort of abstract version of the machine that the programming language presents to you. And so whether the machine can carry it out or not is somewhat incidental. I think that as we move forward, when you're talking about languages of the future, I mean, you know, PhD, like PL theory people are always designing programming languages that we can't use yet for various reasons, or that we could never use because of, so one of my favorite examples, David Mador, who's a French mathematician, created a programming language that solved the halting problem, and you can write programs that count to infinity. And it's all proven that it works. It's just that it requires a computer that's infinitely large, which we can't build in our reality. So that's one type of language, which I think is really interesting from a theoretical side, but it's not something that actually has to do very much with our physical machines. And I think a lot of what I'm doing in the book is sort of getting away from the machine itself to talk about that relationship of logic and language. You know, we're linguistic beings more than we're logical beings, and I think we always carry more into code than we intend to.
So where do you see vibe coding in the spectrum of like a formal programming language or an Esolang, for example?
Yeah, so vibe coding is kind of interesting because it's getting one level sort of removed from code, right? I mean, it's not that hard to imagine people having a series of prompts that becomes the code, that the AI agent becomes part of the interpreter itself. Like, I think we're already sort of moving that direction. And what's interesting to me about that is that they're not consistent, the AI agents, so you can end up with different things each time, which I think most people see as a negative, but I think for me it kind of keeps things a little bit more interesting in that area. I'm not really sure what's gonna happen with that down the line, but one thing I will say is that most Esolangs are created by high school and college kids who are sort of just figuring out they can make a language of their own for the first time, and they might never make another language again. But I think it's really important for people to realize that they have control over that technology, and they can design languages that work for them. They don't have to be sort of reliant on, you know, the handful of languages that were offered. And I think that a lot of that feels very sort of anti-AI, of sort of working away from that and sort of getting more control over the technology. So there's definitely sort of an anti-AI feeling to Esolangs in general. And I'm already seeing some people creating Esolangs as a kind of resistance to those systems.
Anyone else? Kind of a silly question, but if you were to imagine yourself living, 200 years ago, how do you think you would have expressed your creativity?
Okay, that's an interesting question. So I guess you're asking that in the context of Esolangs and programming languages. I think 200 years ago we had maybe it's a little before the full-on industrial revolution stuff, but I think a lot of the time when we talk about programming languages, we talk about them in terms of mathematics, right? That's how most people put the algorithm at the center of programming. But there's some thinkers, Warren Sack has a good book about this, who think about programming more around the sort of automation of tasks, of people sort of carrying out repetitive tasks and having scripts to do that they would follow. And the computer is just the thing that then automates that in some way. I think that you can get to the same, I think a lot of this comes from, you can think of sort of algorithms from that side as physically carrying things out. And pretty much, you don't need the computer to perform a lot of the languages I have described here. So I think, I don't know. I think I would do something around that, around the idea of scripting, around performance. Because the thing of what a program is really, it's a performance score for the computer, right? And we don't need the computer to carry it out. We could carry it out as human beings. So I think I would think about it more along performance. But personally, I like having the computer do it for me.
Hi, Daniel.
Hi.
I've worked a lot with graph-based interfaces or node-based.
Okay.
A lot of software like that, like Touch Designer, for instance. I find graphs to be a really amazing way to interact with information. And I also saw some presenters here at this conference mention graphs as well. Mm-hmm. So have you built any Esolangs based around graphs?
So I don't know Touch Designer. I don't really know what it does. So we're talking about graphs from what aspect? To me, the first thing I hear when you say graph, I think of sort of graph databases where you're creating this sort of relationship between different entities and hierarchies of information. Is that kind of what you're talking about?
Exactly, where nodes can represent objects or functions, and then you connect them, and those connections change the way the algorithm operates.
Mm-hmm. Yeah, we're dealing with those structures most of the time when we're parsing languages, because we always have to build the syntax tree well, you don't always have to, but I generally do for most of my languages. So I'm already kind of thinking in terms of that, in terms of actually carrying out the interpreting of the code. But in terms of representing code as graphs, which I think is more what you're asking, that's not something I've done directly, but I think that could be really interesting, and if that's something you're excited about, you should make an Esolang around it.
I had one myself, actually. For the languages that you've implemented, how have you implemented the interpreter, the sort of parser, lexer for it? Which language would you use for that?
Yeah, so that's a good question. I tend to use languages that are sort of widely used because I want people to understand the code. I think it's a little bit less important now because I feel like there's more. I feel like the open source community is more open to a lot of other types of languages now, and it's okay. So the first thing is, if I can do it on the web, I'm going to do it on the web. So if I can do it in JavaScript, I'm going to do that, because then it's really easy for people to use it. I just create an interface for the browser, and then people can get into it right away without having to download a whole bunch of stuff. So that's always my first choice, but that doesn't always work. For things like folders, it doesn't really make sense, or other things that deal with the file system in some way. So for a while, I was sticking more with very mainstream languages like Python, but I kind of hate Python, so I don't think I'm going to do that anymore. So I'm probably going to go a different direction for my next one.
Amazing, thanks so much. I think we're at time just to get started for the sound check, so Thanks so much to Daniel. Thanks so much to all the speakers, presenters today. Thanks to everyone for coming out and being part of this. Thanks.